Hi dear students, I hope you all are doing great. So let us start the today's session. We have with us today extensive and intensive properties. So if you look here at extensive property, you will find out that it depends upon the size of matter or the quantity of the matter, my dear friends. So let's have a look. So example is here mass. Let's discuss about the mass first. Okay? So my dear friends, if you have a small pebble with you, okay, and you have a big rock, this is a rock. So my dear friends, there is a difference between the two, a pebble and a rock. The difference in size. So who will have greater mass, my dear friends? This pebble will have a greater mass, yes? Or this rock will have a greater mass? Obviously the rock will have greater mass. Who has a bigger size? So if you talk about in terms of size, if we talk about order of size, who has a greater size here? Rock has bigger size. If you talk about order of mass, who has a bigger mass? Rock has a bigger mass. That means when the size of a matter changes, that means you are going from a pebble to a rock. That means size has changed from smaller to bigger. And due to that change in the size, what happens? The mass will also change. So here it has a pebble has a less mass, and this rock, which is of bigger size, has more mass. That means mass changes when the size of the particle changes. That means mass is which property? Extensive property. Remember, my dear friends, so mass is an extensive property. You can go reverse also. If you take one rock, let us suppose you take one rock now. You have taken one rock, break it, just break it. When you break this rock, you will get a fragment here. And what about this fragment of a rock, or a pebble we can say, fragment of rock? This guy has bigger size and this guy has smaller size. So this has more mass and this has less mass. That means the mass depends upon the size of a matter. Yes or no, my dear friends? So that means mass is an extensive property. I hope you have understood, my dear friends. Let's take one more example here about volume. Let us suppose if we talk about volume, and this volume is also an extensive property. Let us see how. See here, my dear friends, if we have again a small, what? Let's suppose we have one brick. Here we have a brick. Okay. And here I have put many bricks together. These are a group of bricks. So this guy obviously has small size and this group will have large size. So here the one brick has obviously a small size and we have so many bricks together here. Okay, so it will have a large size. So obviously this has less mass and this has more mass. That means when size changes, mass will change. Now look at the volume. This brick will occupy less volume because it occupies only this much of volume it will take. But this group of bricks will take this much of volume it will occupy. So if you talk in terms of volume, who occupies more volume? The one brick or the group of bricks? Group of bricks will be having more volume. That means when size of particle changes, the volume will change and the mass of substance will also change. So obviously then volume is also an extensive property. Now have a look. Let's have a discussion here. Let us suppose I will take, this is the volume, let us suppose, this inside. The volume of this particular cube is V. Okay, this is the volume of the cube. Okay. So what happens if I will put one bisector? If I put one, a mirror, or I may put one glass or I may put one cardboard. I can put anything, you know what, in the middle of this particular cube. So this V is actually the value inside the cube. So this V stands for the value of the cube. Okay. Now what I'm going to do this with this cube actually, have a look here. I can put one sheet of glass, or I may put one sheet of cardboard or anything else. So I have divided this particular cube into two equal parts. Then V was the value of the cube. Okay. And now look here, after dividing this cube into two parts, now what is the value here? It will be V by 2, that's half, volume has become half. And this side also the volume has become half. You can put a sheet of, you know what, metal, aluminium here. You can put a sheet of cardboard here. Or you can put anything, whatever your choice. Whatever is your choice, but you have to divide this cube into two equal parts. What was the value here? V. And what is the value after bisecting this cube into two equal parts? The value is V by 2, that is value has become half. So my dear friends, that means here the size was bigger, so value was V. And here we have reduced the size to the half. By reducing the size of a cube to the half, the value has become also half. Then understand that value is also which property, my dear friends? It is an extensive property. If you take, for example, one small grain of sand, yes or no, it will occupy a small value. But if you take a large amount of sand, and that will occupy, you know what, more value. So obviously it's a very simple thing. I hope everybody has understood this particular thing. So this was about extensive properties, and even the number of moles will also depend on what? Quantity of matter or size. Smaller size, less number of moles, bigger size, more number of moles. Internal energy, small object will have less internal energy, bigger object will have more internal energy. Enthalpy, smaller object will have less heat content inside it, and bigger object will have more enthalpy content, heat content within it. Heat capacity, small object can have lesser tendency to absorb small amount of heat. Bigger object can absorb more amount of heat. So heat capacity will also change with respect to size. So this was about extensive properties, my dear friends. Please make note of this. Let's talk about now, my dear friends, intensive property. What is this all about? Its value does not depend upon quantity or size of matter present in a system. That means these properties do not depend upon the size of a matter. But you have seen that mass, volume, number of moles, heat capacity, internal energy, they will change when the size of matter will change, correct or not? But here, these properties, intensive properties, they do not depend upon the quantity or size of a matter. So let us see what are these all about. Have a look. For example, if you take the first one, temperature here. Let us suppose I will take one cube here. And inside that cube, let us suppose there is some water. Let us suppose there is water. Okay. This cube is filled with the water. Or you can also consider it as one container is there. It's filled with water. And inside you can take temperature as T. Let's suppose T is the temperature inside this particular cube. Now let me bisect. Let me divide this cube into two parts. Just like volume I was doing. So if I divide this particular cube into two parts, into two equal parts, I will divide this particular cube. Yes, what happens? Here the temperature is T and here also the temperature is T. Now you have observed that I have reduced the size of the cube, means I have divided the cube into two parts. Let us suppose inside a cube there is water, or there may be any gas also, and there is a temperature T for that. Okay? What happens? Then I bisected, I divided the cube into two equal parts. Then if it is an extensive property, if temperature is an extensive property, what should happen? Temperature should also become half. But you can see here temperature does not become half, temperature remains the same. Yes or no? That means the size of a system or size of a matter does not change the temperature. Temperature remains the same. In other words, I will tell here, temperature is independent of quantity or size of matter. That means temperature does not change. One more way I will make you understand. Let us suppose in one beaker you have a boiling water. Okay? Let's suppose I have a beaker. Inside this beaker I have boiling water is here. Let us suppose the temperature inside this beaker for this boiling water is, let us suppose, 100 degrees Celsius. So what is the temperature inside the beaker? 100 degrees Celsius, correct? Let me take from this beaker, I will take little amount of water. So what I am doing? Transfer, let us suppose 20, let us suppose this boiling water is actually here 1000 ml, that means 1 liter. 1 liter of boiling water we have here. Now I have transferred 10 ml into, let's suppose, test tube. Let's suppose this is a test tube and I am transferring 10 ml from here into this. So now how many ml I have here? Here also I have boiling water. How many ml I have here? 10 ml. Here I have 1000 ml. So out of 1000 ml I have taken out how many ml? 10 ml. What is left here? 990 ml is left here. Okay. What is the temperature inside this particular beaker? Let us suppose. And this was 100 degrees Celsius. After transferring 10 ml here, now the size or the volume of the substance has changed. Volume has changed. What is the remaining volume here? 990 ml. And what is the volume here? 10 ml, correct? So what happens? What about the temperature? Temperature is here also 100 degrees Celsius. You can use the thermometer and check the temperature here. It will be 100 degree here also 100 degree. That means temperature does not change. Size of the matter has changed. Here you have 1000 ml of water. Then you transfer 10 ml here. What is the remaining here? We can tell you have here 990 ml of water. And here you have only 10 ml of water. That means volume has changed. Yes or no? So volume is basically which property? We know that volume is nothing but an extensive property. But we are not talking about volume here. We are talking about temperature. What was the temperature here? 100 degree. And what is the temperature here? Here the temperature is, my dear friends, 10 degrees or 100 degrees. 100 degrees. That means temperature does not change. In the same way I will tell you, you take a sample of water, yes I know, from ocean and check its temperature. Let us suppose if it is 20 degrees. Then you put the thermometer into the ocean and check the temperature. You will find out the same temperature will be there. That means temperature does not depend upon the size of matter or quantity of matter. It is independent of it. So it is which property, my dear friends? It's an intensive property, remember. So I hope everybody has understood. So let's go further and talk about one more factor here. One more factor is here, density. If you look here, density is equal to mass upon volume. And we know that density is nothing but it's an intensive property, my dear friends. I will tell you how. It's an intensive property. And this mass, if you talk about this mass is an extensive property. Just now I told you, extensive property. And this volume is also an extensive property. So the ratio of two extensive properties gives you the intensive property. So let us explain how the density is basically an intensive property. Density. Yes. If you go and check the density of, let's suppose you are going to land. Let's suppose you have a piece of land, okay, and you are going there and you have to check the density of a land. So for checking the density of a land, you need not to check the density of the entire land. Yes or no? Whatever will be the density of a small sample of soil, that will be the density of the land. That means density does not depend upon the size of the matter. Yes or no, my dear friends? Because whatever will be the density of the small sample of soil, yes or no, same will be the density of the land. That means the density is basically the intensive property. It does not depend upon the size of matter. If it depends upon the size of matter, then the density of the sample of a soil should be different than the huge amount of soil. Yes or no? So whatever is the density of a sample of soil, same is the density of the entire land. So understand, density does not change with the size of matter. So it is obviously an intensive property. So obviously, my dear friends, if you look here, the pressure is also an intensive property. Whatever the pressure is present here in this area or in this volume of atmosphere, let's suppose I will take some volume of the atmosphere. Whatever the pressure is here, the same pressure is here also. The same pressure is here also. That means here also the pressure does not depend upon the size of matter. Whatever the pressure is present in this room, the entire room, the same pressure is present in that corner also. That means, my dear friends, pressure is also an which property? Intensive property, does not depend upon the size of matter. If it depends upon the size of matter, then pressure will keep on changing. Yes or no? It does not change in a particular area. I am talking about a particular value. I hope you have understood. And now here, look here. Here I was having, in case of extensive property, I was having heat capacity. When the size of matter will change, its heat capacity, tendency to absorb the heat will also change. But here I am not talking about heat capacity. Here I am talking about molar heat capacity. It is the heat capacity of 1 mole of a substance. So it also does not depend upon the size of the matter. If you tell only heat capacity basically means the tendency of a substance to absorb the heat, correct? If small substance is there, it will absorb less heat. If bigger substance is there, it will absorb more heat. That is heat capacity, so it's an extensive property. But when you look at the molar heat capacity, here size does not matter. Why? Because we are talking only about the capacity of 1 mole of a substance. That means how much of heat 1 mole of a substance can absorb. Remember that. So molar volume. If we talk about just volume is also which property? Extensive property. Because when size of particle will increase, the volume will also increase. But here I am talking about molar volume. Molar volume is only the volume with respect to 1 mole of a substance. So it also does not depend upon the size. Because it's confined to 1 mole. Molar volume. Molar heat capacity is confined to 1 mole. So these properties are our intensive properties. Volume is extensive property, but molar volume is intensive property. Yes? When size of matter will change, the volume can also change. But molar volume is basically with respect to 1 mole of a substance. So it does not depend upon what? Size of a matter, my dear friends. Let us suppose in simple words, I will make you understand like this. If you have molar volume of any substance, like 1 mole is occupying, let us suppose, 22.4 liters of volume. 1 mole of any gas occupies 22.4 liters of volume, my dear friends. So that is called as molar volume. But if I don't write down molar volume, if I write down just volume, then volume is an extensive property. But if it is a molar volume or molar heat capacity, molar concentration, molarity, pH, these are all intensive properties. Please remember that and make note of this. So my dear friends, let's have a look here. We will talk about zeroth law of thermodynamics now. This law states that when 2 objects are in thermal equilibrium with third object, then they will be in thermal equilibrium with each other as well. Very simple. Have a look. Let's take the 3 objects here, A, B and C. Correct, my dear friends? And let us take it as a diathermic wall. That means conduction is possible here. Conducting wall, we can also call it as conducting wall. Heat transfer or exchange is possible. So my dear friends, let us suppose A is in thermal equilibrium with B and C is also in thermal equilibrium with B. So I'll write down here, A is in thermal equilibrium with B. So there is a thermal equilibrium between A and B. What is the meaning here? That heat flows from A to B and from B to A. They are in equilibrium. So this is the flow of the heat in both directions. So they are in equilibrium. Now second statement is that, look at C here. C is in thermal equilibrium with B. Thermal equilibrium with B. So my dear friends, B is common here. So now heat will flow from B to C and C to B. That means equilibrium. These marks are actually, these arrows will indicate the equilibrium. Okay? State. Half arrows, forward and backward. So that is equilibrium state. A is in thermal equilibrium with B and C is in thermal equilibrium with B. A is in equilibrium with B and C is also in equilibrium with B. Then according to this law, when A is in thermal equilibrium with B and C is also in thermal equilibrium with B, which means that A and C will be also in thermal equilibrium with each other. Hence, A and C will also be in thermal equilibrium with each other. So now my dear friends, you will be thinking that how does this thermal equilibrium has been achieved actually. Look here my dear friends, if I have with me two objects or two substances and this is diathermic wall here. Let us suppose this is hot object or hot substance and this is cold here. Let's suppose here we have hot water and here we have cold water. Or you can also you can have your hot gas and it's a cold gas here. Okay, means in terms of temperature I am talking about. Okay, so what will happen? The heat will always flow from where to where? From the hotter object to the colder object. So heat flows from hotter body to colder body. So it will keep on flowing. The heat will keep on flowing till the equilibrium is achieved. So look here my dear friends. Now look here my dear friends, if it is a hot object or hotter object and this is cold object here. So heat will flow from hotter to cold. So there is a flow of heat from hotter object to the colder object. Then a time will come that the heat is flowing in both the directions. What is the meaning? Now the temperature of both the substance has become equal. Because when heat keeps on moving from hotter to cold objects, a time will come that the temperature of both of the substances or both of the objects will become equal. And that is called as thermal equilibrium, my dear friends. Look here, for example, if the, let us suppose temperature was here 20 degrees Celsius and here it was, let us suppose temperature was here 10 degrees Celsius or whatever it may be. So the heat will flow from this object to this object, from hotter object to colder object. Now when they are in equilibrium with each other, let us suppose here the temperature is here 15 degrees Celsius and here is also 15 degrees Celsius, and this state is called as equilibrium state, and heat is flowing in both the directions, my dear friends. I hope you have understood the zeroth law of thermodynamics. Remember always that heat will always flow from the higher concentration to the lower concentration, from hotter object to the colder object. When heat keeps on flowing from hotter object to colder object, what happens? A time comes when the heat content of both the objects become equal, and when that becomes equal we call it as thermal equilibrium. And you have also understood the definition here that when two objects are in thermal equilibrium with third object, then those two objects are also in thermal equilibrium with each other. I made you understand that here. Please make note of this. So dear friends, let's have a look at the internal energy. I told you last time also, internal energy can be symbolized or it can be denoted either by letter U or by E. So you can use letter U or E for the internal energy. But in your NCERT chemistry book, we will be using mostly the U symbol for the internal energy. Okay, my dear friends? What is this internal energy actually, my dear friends? Internal energy is the sum of all the energies associated with the system. It is very much dead impossible to calculate the exact value of the internal energy, because there are so many different types of energies associated with a particular system. Let us suppose if you take me as a system, there are so many different types of energies within my body, different types of energies, and the sum of all those energies will be the internal energy of mine, my dear friends. So if you look here, the sum total of all the energies, whether it's a chemical energy, mechanical energy, electrical energy, and there are many other types of energies as well associated with the system, we call them as, that is the internal energy of the system. And remember, last time I told you something. Some important points I will write down here. Just now we discussed one thing, if you remember, that I told you that internal energy is an extensive property. What is the meaning of this? That its value depends upon the size of matter. That means a smaller object will have less internal energy and bigger object will have more internal energy. So my dear friends, internal energy is an extensive property as it changes with the size of the matter. Correct? Second point. Internal energy is a state function, my dear friends. Internal energy is a state function. That means its value depends upon initial and final state of a system, which means its value depends upon initial and final state of a system. Final state of a system. And I wrote here, my dear friends, that it's an extensive property. Means it depends upon, its value depends upon the mass of a substance or the size of a substance. Second thing I wrote, internal energy is a state function. Its value will depend upon the initial and final state of a system. Have a look here. If I will represent this is delta U. Delta U is nothing but its change in internal energy. Change in internal energy. And we know that internal energy is basically a state function. It's a state function. So its value will be given by final internal energy minus initial internal energy of a system. So this is final internal energy of a system minus initial internal energy of a system. We will get the change in internal energy. So this delta U will represent that internal energy is which function? A state function. Smaller object will have lesser internal energy and bigger object will have more internal energy. That means internal energy is a extensive property. Yes or no? And the value of internal energy is only calculated by taking in consideration initial state of a system and final state of a system. So that means our internal energy is a state function, not a path function. Please remember that particular point. If we talk about now, how does the internal energy of the system can be changed? How can you change the internal energy of a system? Very easy. So I have written some of the facts here. So internal energy of the system can be changed by following things. What are those things? Let us see one by one. The first thing, heat exchange between system and surroundings. This can change the internal energy of the system. Okay. Second thing, work done on the system or by the system. This can also change the internal energy of the system. Third thing, matter exchange between system and surroundings. This will also change the internal energy of the system. So my dear friends, in next class we will be discussing in detail that how does these factors change the internal energy of the system. But right now I will give a very little idea about these three factors. Okay, so have a look here. Heat exchange between system and surroundings. Let us suppose this is our system, correct? Inside this we have, let us suppose, gas is inside, correct? And the heat is coming from the system into the surroundings. So this guy is our system here. So heat is liberated by the system into the surroundings. Yes or no? So gas is losing the heat to the surroundings. That means internal energy of gas will decrease. Yake? Because it loses heat to the surroundings. So this guy is losing the heat to the surroundings. So if a system loses the heat to the surroundings, okay, then the internal energy of the system will obviously decrease. Now, reverse is also true. What is the reverse thing? If reverse thing happens, if the heat comes from surroundings into the system, that means surroundings should be at high temperature and system should be at low temperature. Then only heat will flow from surroundings to system. Correct? In this case, what happens? Internal energy of the gas will increase now. Internal energy of gas will increase because it loses or gains now, because it gains heat from the surroundings. So reverse thing will happen. So if you are losing the heat, understand that your internal energy will decrease. But if you gain the heat, absorb the heat, your internal energy will increase. So by losing heat, internal energy decreases of a system, and by gaining heat, internal energy of the system will increase. That's a common sense. Now let's go further to the second point. Let us suppose if you are doing some work, if you do some work, what will happen to your energy? Let's suppose I am doing some work. What will happen to my energy? My energy will decrease because I am doing work. So obviously, work done on the system and by the system. First of all, I will tell you here, by the system. Let us suppose I am a system. I am doing some work. When I do some work, what will happen? My energy will decrease because I am doing work. That means internal energy of the system will decrease when work is done by the system. But now, if the work is done on the system, yes or no, then the internal energy of the system will increase. Now third point, matter exchange between system and surroundings. My dear friends, if we have an open system here, this is open system, and let us suppose any gas is entering here. Nitrogen gas enters inside. Let us suppose carbon dioxide gas enters inside. In this system, let us suppose we have water. We have here water in this system. This nitrogen gas will dissolve in the water. So water will have some internal energy, correct? But when nitrogen gas from atmosphere, from surroundings, it dissolves in water. Carbon dioxide gas also dissolves in water. This is matter exchange. And matter is coming from where? Matter is coming from the surroundings and entering into the system. What is present in the system? Water. Water is absorbing the matter from the surroundings. So now, water was there in the system, open system. Now matter is also coming from outside into the system. That means the mass of the mixture inside the open system will increase. Now water is not present alone here. What is present here in the open system now? Water and which gas? Nitrogen gas and carbon dioxide gas is also present. That means the mass, the quantity of substance inside this open system will increase or decrease? Increase. That means, my dear friends, when matter increases, the internal energy of the system will also increase. There was only water. Then which gas has come inside? Nitrogen gas and carbon dioxide gas. Because of the presence of nitrogen and carbon dioxide gas into the water, they dissolve in the water. Okay? So the quantity of matter has increased now. Because now there is water plus nitrogen gas plus carbon dioxide gas in the open system. So the quantity of matter has increased now. Yes, that means the internal energy of the system will also increase. Remember that point. And reverse is also true. The reverse is like this, my dear friends. Let us suppose I have here hot water or boiling water we have here. Let's suppose we have a boiling water. What will happen? This boiling water will change into the vapors, and vapors will enter into the surroundings. These are the vapors. So now let us suppose when I have a boiling water in this open system, okay, and this boiling water is changing into vapors. Vapors are nothing but matter. So matter is coming from the system into the surroundings. That means water vapors are coming out. That means matter is going from system to surroundings. That means this quantity of water inside will become less, because this boiling water its quantity is lost in the form of vapors. Vapor is a matter, it's a water vapor obviously. So vapors are coming, or matter is exchanged between system and surroundings. System is losing the matter and surroundings is gaining the matter in the form of water vapors. So the quantity of the water in the open system will decrease. When quantity of water in the open system decreases, then what happens? Its internal energy will also decrease. So remember that, my dear friends. These three factors will change the concept of internal energy. They will either increase the internal energy or decrease the internal energy. In next class we will discuss them in detail. Have a good time. Take care of yourself. Yes.